Lecture 3: Data Storage in Memory and Number Representation. How does a computer store data? Well, this could be either very easy or very complicated. Information is stored in a number of places using different technologies for each purpose. The hard disk contains all permanent data including the operating system, which gives you the means to communicate with the hardware in the computer, and the user interface, which includes all the files necessary to display items on the desktop, and the way that it has been configured to work with your programs. The random access memory is the temporary storage to work on constantly changing data, which is fast memory and includes how to display the items you see on the screen. This memory is volatile, disappears when power is removed, and can be updated almost as instantly as you see it. The information is stored magnetically on rotating platters inside the disk that is hermetically sealed from the environment. More recent storage has been solid state, storing a charge in an insulated well in a minute space and has no moving parts. There is also two other types of memory that store the configuration data for the hardware: CMOS or EEPROM at boot up, and some very fast immediate cache memory running at the same speed as the microprocessor. This picture shows the computer memory hierarchy. If we check at the bottom of the picture, memory size is bigger and it can store data for a long period. But these memories are slower. For example, tape and hard drives. If we look up in the triangle, the size of the memory will get smaller, and these memories can store data for a short period. But these kinds of memories are really fast to retrieve and temporarily store the data, such as registers and caches. Memory hierarchy. The memory hierarchy separates computer storage into a hierarchy based on response time. Since response time, complexity, and capacity are related, the levels may also be distinguished by their performance and controlling technologies. Memory hierarchy affects performance in computer architectural design, algorithm prediction, and lower level programming constructs involving locality of reference. Designing for high performance requires considering the restrictions of the memory hierarchy, such as the size and capabilities of each computer. Each of the various components can be viewed as part of a hierarchy of memories in which each member is typically smaller and faster than the next highest member of the hierarchy. There are four major storage levels: internal storage, main storage, online mass storage, offline bulk storage. This is a general memory hierarchy structuring. Many other structures are useful. For example, a paging algorithm may be considered as a level for virtual memory when designing a computer architecture. One can include a level of nearline storage between online and offline. Data storage. Data is converted to simple numbers that are easy for a computer to store. Then numbers are recorded by hardware inside the computer. After this, the numbers are organized, moved to temporary storage, and manipulated by programs or software. Hard disk drives use mechanisms to store numbers. Computer data storage is a technology consisting of computer components and recording media that are used to retain digital data. It is a core function and fundamental component of computers. The central processing unit of a computer is what manipulated data by performing computations. In practice, almost all computers use this storage hierarchy, which puts fast but expensive and small storage options close to the CPU and slower but less expensive and larger options further away. Generally, the fast volatile technologies are referred to as a memory, while slower persistent technologies are referred to as a storage. Data organization and representation. A modern digital computer represents data using the binary numeral system. Text, numbers, pictures, audio, and nearly any other form of information can be converted into a string of bits or binary digits, each of which has a value of 0 or 1. The most common unit of storage is the byte, or equal to 8 bits. A piece of information can be handled by any computer or device whose storage space is large enough to accommodate the binary representation of the piece of information, or simply data. For example, the complete works of Shakespeare, above 1250 pages in print, can be stored in the about 5 megabyte 40 million bits with 1 byte per character. Data are encoded by assigning a bit pattern to each character, digit, or multimedia object. Many standards exist for encoding, such as character encoding like ASCII, image encoding like JPEG, video encoding like MPEG-4. By adding bits to each encoded unit, redundancy allows the computer to both detect errors in coded data and correct them based on mathematical algorithms. Errors generally occur in low probability due to random bit value flipping or physical bit fatigue. Loss of the physical bit in storage of its ability to maintain distinguishable value 0 or 1, or due to errors in inter or intra-computer communication. A random bit flip is typically corrected upon detection. A bit or a group of malfunctioning physical bits is typically automatically fenced out, taken out of use by the device, and replaced with another functioning equivalent group in the device. Where the corrected bit values are restored, the cyclic redundancy check method is typically used in communications and storage for error detection. A detected error is then retired. Data compression methods allow in many cases to represent a string of bits by a shorter bit string and reconstruct the original string when needed. This utilizes substantial less storage for many types of data at the cost of more computation. Analysis of trade-off between storage cost saving and cost of related computation and possible delays in data availability is done before deciding whether to keep certain data compression or not. For security reasons, certain type of data may be kept encrypted in storage to prevent the possibility of unauthorized information reconstruction from chunks of storage snapshots. What is the difference between memory and storage in computers? Understandably, many computer users consider memory and storage to be the same thing. Those who realize that there is a difference between the two often cannot identify this difference. If you are unsure about the difference between memory and storage in computers, this part of the lecture will enlighten you. Memory. The term memory refers to the component within your computer that allows you to access data that is stored for a short term. You may recognize this component as DRAM or dynamic random access memory. Your computer performs many operations by accessing data stored in its short-term memory. Some examples of such operations include editing a document, loading applications, browsing the internet. The speed and the performance of your system depends on the amount of memory that is installed on your computer. If you have a desk and a filing cabinet, the desk represents the memory of your computer. Items you will need to use soon are kept in your desk for easy access. However, not much can be stored in a desk due to its size limitation. Storage. Whereas memory refers to the location of short-term data, storage is the component of your computer that allows you to store and access data on a long-term basis. Usually storage comes in the form of a solid-state drive or a hard drive. Storage allows you to access and store your applications, operating systems, and files for an unlimited period of time. While the desk represents the computer's memory, the filing cabinet represents the storage of your computer. Items that must be kept yet would not necessarily be accessed soon are stored in the filing cabinet. Due to the size of the filing cabinet, many things can be stored. An important distinction between memory and storage is that former clears when the computer is turned off. On the other hand, storage remains intact no matter how many times you shut off your computer. Therefore, in the desk and filing cabinet similarity, any files that are left on your desk when you leave the office will be thrown away. Everything in your filing cabinet will remain. Bits, bytes, and words. The most fundamental unit of computer memory is the bit. A bit can be a tiny magnetic region on a hard disk, a tiny dent on the reflective material on a CD or DVD, or a tiny transistor on a memory stick. Whatever the physical implementation, the important thing to know about a bit is that, like a switch, it can only take one of two values. It is either on or off. A collection of 8 bits is called a byte, or in the majority of computers today, a collection of 4 bytes or 32 bits is called a word. A bit is a binary digit that represents one of two states. The concept of a bit can be understood as a value of either 1 or 0, on or off, yes or no, true or false, or encoded by a switch or toggle of some kind. While a single bit on its own is able to represent only two values, a string of bits may be used to represent larger values. As the number of bits composing a string increases, the number of possible 0 and 1 combinations increases exponentially. While a single bit allows only two values combination, and two bits combined can make 4 separate values and so on. The amount of possible combinations doubles with each binary digit. Grouping with a specific number of bits are used to represent varying things and have specific names. A byte is a bit string containing the number of bits needed to represent a character. On most modern computers, this is an 8-bit string. Because the definition of a byte is related to the number of bits composing a character, some older computers have used a different bit length for their bytes. In many computer architectures, the byte is used to address specific area of memory. For example, even though 64-bit processors may address many 64 bits at a time, they may still split the memory into 8-bit pieces. This is called byte addressable memory. Historically, many CPUs read data in some multiple of 8 bits. Because byte size of 8 bits is so common, but the definition is not standardized. The term octet is sometimes used to explicitly describe an 8-bit sequence. Each individual data value in a dataset is usually stored using one or more bytes of memory. But at the lowest level, any data stored on a computer is just a large collection of bits. For example, the text hello would take up 5 bytes of storage, one per character. The text 12345 would also require 5 bytes. The integer 12,345 take up 4 bytes or one word, as would the integer 1 and 1, 2, 3, 4, 5, 6, 7, 8. The real number 123.45 would take up 4 or 8 bytes, as would the value 0.000123445 and 1234500.0. A nibble is a number composed of 4 bits. Being a half byte, the nibble was named as a play on words. A person may need several nibbles for one bit from something. Similarly, a nibble is a part of a byte because 4 bits allow for 16 values. A nibble is sometimes known as a hexadecimal digit. Computer number format. A computer number format is the internal representation of numeric values in digital computer and calculator hardware and software. Normally, numeric values are stored as grouping of bits, named for the number of bits that compose them. The encoding between numerical values and bit patterns is chosen for convenience of the operations of the computer. The bit format used by the computer's instruction set generally requires conversion for external use such as printing and displaying. Different types of processors may have different internal representation of numerical values. Different conversions are used for integer and real numbers. Most calculations are carried out with number formats that fit into a processor register. But some software systems allow representation of arbitrarily large numbers using multiple words of memory. Binary number representation. Computers represent data in sets of binary digits. The representation is composed of bits, which in turn are grouped into large sets such as bytes. This table illustrates the binary to octal values. This table shows the number of values for a bit string. A single word of memory contains 32 bits, so it requires 32 digits to represent a word in binary form. A more convenient notation is octal, where each digit represents a value from 0 to 7. Each octal digit is the equivalent of 3 binary digits, so a byte of memory can be represented by 3 octal digits. Binary values are pretty easy to spot, but octal values are much harder to distinguish from normal decimal values. So when writing octal values, it is common to precede the digits by a special character such as leading 0. As an example of octal form, the binary code for the character A splits into triplets of binary digits like this: 01, 000, 001, so that octal digits are 101, commonly written 0101, to emphasize the fact that these are octal digits. An even more efficient way to represent memory is hexadecimal form. Here, each digit represents a value between 0 and 16, with values greater than 9 replaced with the characters A to F. A single hexadecimal digit corresponds to 4 bits, so each byte of the memory requires only 2 hexadecimal digits. As with octal, it is common to precede hexadecimal digit with a special character such as 0x or hash. Binary form for the character A splits into two quadruplets: 0100, 0001. The hexadecimal digits are 41, commonly written as hash 41. Another standard practice is to write hexadecimal representations as pairs of digits, corresponding to a single byte separated by spaces. For example, the memory storage for the text "just testing" take 12 bytes could be represented as follows. 6A 75, 73, 74, 20, 74, 65, 73, 74, 69, 6E 67. When displaying a block of computer memory, another standard practice is to present three columns of information. The left column presents an offset and a number of indicating which byte is shown first on the row. The middle column shows the actual memory contents. Typically in hexadecimal form, the right column shows interpretation of memory contents, either character or numeric values. For example, the test just testing is shown below. Complete the offset and character display columns. 6A 75, 73, 74, 20, 74, 65, 73, 74, 69, 6E 67.